Welcome back to the DemystifySci Podcast. Today we are sitting down with Dr. Alexander Unzicker, who is famed for his YouTube channel, Real Physics with Alexander Unzicker. And we have had Unzicker on the show so many times. I think this is our fourth conversation. And if you want to check out the rest of those conversations, go ahead and head over to that playlist in the corner here. And tear into previous ideas. We were exploring the liquid sun, the material congruence between deformations in material lattices and electromagnetics, so exploring potential advancements of ether ideas. We were exploring the role of math versus materialism in physics. We've been all over the place. And today we're talking about the constants of nature, the fundamental constants of nature. So things like speed of light, gravitational constant, fine structure constant, and Dr. Unzicker has been tearing these apart, trying to simplify them and understand why they emerge.
The reason that we wanted to have this conversation is because it's a follow-up from something that we were talking about with Thad Roberts, which Thad has this physics monastery in the desert where they're trying to look through all of the equations that have these constants and see if they can relate the constants to one another. And over the course of having the physics conversations that we've had, we've really come upon this question of, well, what does it mean for something to be a constant? What does it mean when somebody says that they want a theory of everything? What do we reduce our equations to? What are the pieces that we can simplify? What are the pieces that are fundamental? And so over the course of almost 2 hours, a little bit more, I think, we go through all of the different constants of nature, the ones that Unzicker thinks can be simplified versus the ones that can't be, versus those biggest questions that remain, which for Unzicker is, what is space-time? Like, why, when you reduce everything, are you still left with distance and time? Is it possible to resolve further and drill down to the bottom of the universe and to find that there is some hidden mathematical relationship that gives rise to these? If you've listened to enough of the podcast, you know that we come down on a different side of this. And so what really this conversation uncovers is almost a metaphysical divide. Like, what do you see at the bottom of nature? Is math fundamental and it emerges and it is something that needs to be figured out mathematically? Or is the math the readout of something that needs to be figured out because there is a thing there that is giving rise to the math? And so
Things in motion.
Things in motion. Shiloh's always correcting me about this, but it's true. Like, it's not just things. It's the motion of the things and their relative relationships. And so Unzicker's the best person to have this conversation with because he spends so much of his time thinking about it and spends so much time trolling the old literature and seeing how people have resolved these questions. And yeah, it was a really great time.
Big thank you to our Patreon supporters. You guys are the lifeblood of this project. You are keeping us alive, literally. And so if you have just $1 or $2 to spare, come over to patreon.com and support the project. You can join our community too and hang out. We do a weekly chat all together and really just explore where we should be going with these investigations, who we need to talk to, and what we're missing out on. There's only 2 of us here, and we depend on everybody in our community to bring us all the nuggets that need to be investigated.
And if you have already supported us on Patreon or you are looking for other ways, then you should come to our conference this April. We are hosting it in Austin, Texas on April 7th and 8th. And we're going to have 2 days of talks, workshops, conversations, and hangouts with all of the people that are interested in the ideas that we present on the podcast. Tickets are for sale up here. So come by the Eventbrite and register today.
And if you've already done all of that or none of that, say you don't have any money, no problem. Share the podcast with somebody. Give us a good review over on one of the podcast stores. And, subscribe, like, support it in ways that are completely free. They all really add up, and they result in us getting better and better guests for this show. And we really, really appreciate it. Otherwise, let's go talk to Alexander.
The scientific revolution starts now.
The DemystifySci Podcast.
Let us see in the dark.
We've covered a lot of ground with you already, and we spent some time talking about Pierre's work, and then we talked about the material representations of, well, let's say lattice dislocations, things like this with respect to the ether last time. Yeah, where are you headed now? Obviously, you were most recently working on this Machian conception and the variable speed of light, which we've touched on before, but we could talk more about those as well. But maybe you can just tell us what's on your mind lately these days.
No, I mean, the Machian stuff and the variable speed of light is certainly something very, very exciting. And that's, of course, always my focus of interest. But I would say in a more general context, even more generally, if we talk about fundamental physics, this is a part of a more general discussion I would like to do. Yeah. And well, I mean, maybe we can start with a methodological sideline, because what do we want to achieve as humanity? Understanding of nature, understanding fundamental laws, and people are talking about theories of everything, and there is the mainstream, and there are string theorists, and there are outsiders, I don't know, like Eric Weinstein, and I think we haven't pondered properly the question: what do we want to achieve? What the goal is here? What do we consider even progress? You know, and
why should people care, right? I think that's a really important question with fundamental physics. It's like, how is this?
Why should people care? I mean, well, my answer would be physics has done something for humanity, for civilization. The development of civilization is clearly related to the discoveries of fundamental physics. If you go back to the Middle Ages, and then you have 1600, 1700, there's a clear change in civilization. I mean,
just from a technological standpoint,
whether you find it good or not, it's still another discussion. But there is the progress of civilization is clearly related to fundamental physics discoveries. And I don't want to, of course, it's not that people wanted to bring ahead civilization. They were just curious about, no? I mean, these guys like Heinrich Hertz, he was just curious to what's the speed of light, and he didn't want to invent mobile phones or television or whatever. So, yeah, but coming back, I think, the curiosity is there. There are many people curious, and many people would like to find out something about fundamental physics. Even Elon Musk, he what he does when he's interested, he starts a company and let's do fundamental physics with AI. So I think the curiosity is here. That's a good thing. But we still don't know. We don't have a plan how to proceed. Okay, and that's what I think that's the first topic we need to address here. And David Lindley, the science writer, says, isn't it strange that everybody is searching for a theory of everything, but nobody has a plan how that theory could potentially look like, but everybody is convinced at the same time that he would recognize it once we have it. Okay, so what are the features? What do you think? What must the theory of everything do? Okay. So
do you have an answer to that, or do you have an because I think that's a really useful place to start, right? Because physics is, the way that I see it, is mythological. Like, the science is the mythology of today. I've been trying on this idea that there's not that much difference between the myths that we told ourselves prior to the Age of Reason and the myths that we tell ourselves after the Age of Reason, except for the foundational metaphysics. Prior to Descartes, the foundational metaphysics was Aristotelian and Platonic. It's this idea that you have the realm of forms that are somewhere else, and they somehow, through a nebulous collection of actions, are creating the reality that we live in. And so that's like a very churchy, religious sort of thing. It's the realm of gods and angels, and the realm of hell. after the Age of Reason, we have a different metaphysics, which is that no, we tell stories that have natural causes. We no longer point to the supernatural. And I think
Yes.
that's the innovation that changes at the 1600s, because instead of going to gods and angels, we're now, okay, there's the natural sciences, and we start to develop that. And so physics is valuable precisely because it's mythological. It is the story that we tell ourselves about creation, about why things happen. It's the cause and effect of the universe that must be significant to people because everybody wants to live in a world that they understand. And right now, theoretical physics is very much a world that is not meant for you to understand. Like you watch videos about, the Big Bang or something.
Yeah, I was gonna say when you're
I
talking
like
about
very
why
much this.
should people care about this, it's like, well, there's actually something deeply important about being able to understand the world around you. Like the definition essentially of insanity or something is not being able to put any order onto the world that's around you, right? Like people who are schizophrenic, they're not actually able to order the different sensory perceptions in a way that is congruent with what's actually happening. And so if you take that to its logical antithesis, what you need to do to be most sane is to have a really good map of the universe as far as you possibly can reach at some point. So I guess that's the aim of the theory of everything.
Well, I try not to focus on the insanities of modern physics, about the sanities, let's say, what is sane and what is healthy. But I think it's a very good point, Anastasia. You want to understand, and you had these old godness and myths, and I think my argument is that some myths have survived into present day physics and have taken the role of the godness. And these are the constants of nature. Because, originally you couldn't explain something, so you postulated a god of the thunderstorm, and a god of the light, and a god of the sea, and so on. So it's more subtle, but we still have the realm of the unexplained, and which is declared as unexplainable by the by most physicists. Most leading physicists would even argue that certain things are not explainable, and these are the constants of nature. So this is a very interesting phenomenon, I think. Almost, psychologically also. Everybody lives, every trained physicist knows about there are certain constants of nature, gravitational constants, speed of light, Planck's quantum of action, and they just put up with it. No question. It's here. It's okay. Even mathematicians, strangely, you need a lot of math, and math is your toolbox as a physicist, and also mathematicians. In my view, they don't complain enough about this strange habit of these constants of nature. Where do they come from? You, as a physicist, and this is my argument, you got to explain that. You want to understand things. That's your business, at least to try. I'm not saying it's very easy. It's very, very hard. But this is I think the royal road to an understanding of fundamental physics. Try to understand fundamental constants. I can give also some other arguments, I think, in favor of that. But just let that sink in. These are really the gods of modernity. Why is it 6.67 times 10 to the minus 11 and so on, cubic meters over kilogram second squared? Why is that? Why it's not 5? Why it's not orders of magnitude away from that strange value? You have to answer this.
Yeah, that seems like second nature for more boring sciences. Let's say, like in material science, you might look at a material and see how stiff it is and gauge that with something like a Young's modulus, like this constant of proportionality. And then you could say, well, why is it this stiff? And you could start looking at the lattice arrangement, the different bond strengths of those atoms inside of the lattice, the positions that they're free to deform into. Like all of these things could go into explaining why that constant has the value that it has. But in some of these more exotic topics, right, like gravitation or quantum of action, like you said, what are we scaling in each one of those phenomena? And then why does it scale the way that it does? Seems to be what this boils
Yes.
down
Yeah.
to.
Yeah.
And
It's an interesting
and also
sorry.
universality, I think, is also universality
Yes,
is
yes,
important, right? Because
yes.
when you
Yeah.
talk about something like Young's modulus,
Ubiquity.
it's not a
Is-
universal. It's a universally useful modification of an equation, but each material will have its own modulus, and so it's
Yes,
not like
but
there's
yeah,
one.
the interesting the example he brought up is interesting because, I mean, of course, we have successful applied physics, and you're doing material science, and that's your everyday life. So you don't really have the necessity to go into this. Why is that modulus like that? And couldn't do you couldn't do practical science, solving practical problems. But in this case, as a matter of principle, it's possible that, I mean, if you know precisely how the electron works, if you know precisely the lattice, the structure of the lattice, if you know precisely the temperature and so on and so forth, as a matter of principle, I think everyone would agree that these Young's modulus or whatever could be computed. Okay, I mean, there is a technical hurdle that it's just too complicated to deal with all this. If you have dislocations or whatever, could be very complicated. Could also be very, very complicated, and people have not done it yet. For example, computing the boiling point of water, ordinary water. Yeah, it's something very simple. You think, but it's the devil is in the detail. You can't do that. But I would say these are technical difficulties that one day we might overcome. There is no barrier as a matter of principle that why shouldn't we be able to compute the boiling temperature of water or the Young's model of iron and whatever substance. Okay, but you're right. Physicists in a way are used to not to ask these questions. But once you do fundamental physics, you have to. And there are a couple of arguments, and I would say one argument is clearly simplicity. Good laws of nature are simple, and complicated theories have always resulted in contradictions, or I mean, history told that complicated stuff did not work at the very end, like epicycles. So, but this might be, you might say that, okay, that's your personal fancy. You believe in simplicity. Who told you? The particle physicist emailing me. Who told you that? I mean, it should be simple. Yeah? There is historical evidence, because I would claim, but that's kind of a bold claim, but let's say most of the revolutions, maybe not all, most of the revolutions can be linked to elimination of physical constants, of constants of nature. Famous example, electrodynamics of Maxwell, corroborated by the experiments of Heinrich Hertz. And eventually we had this, the speed of light squared is 1 over epsilon naught mu naught, the electric constant. Wow, that's the unification of optics and electromagnetism. And you had 3 constants of nature before, okay, C, epsilon naught, mu naught. And with this equation, you had only 2. So I think that's the nicest example, because you have just one constant of nature explained, and think about what it did to civilization. Okay. So this is, yeah.
And the argument that you've made for the explanation of big G is a Machian argument, where you've pulled from these papers, where you basically show that if you take the mass of the universe and its influence on local masses, that you can derive this proportional relationship that gives you this very, very small constant.
Yeah.
And that's... Okay, so what is the next step with that? To tie it back to what you were saying earlier about the goal of physics. Because right now we still have a really nebulous mechanism there? Like, what is the mechanism by which the mass of the universe influences everything?
Yeah, I mean, very good. I mean, you transported that to, I mean, the formula with the electrodynamics that is settled history. Okay, so everyone would agree on that. And you already, said that. Okay, logically, the next step, or let's say an analogous step, would be okay. Let's compute the gravitational constants. This is our business. Okay, but I mean, you need to arrive there. That's what I'm saying. Let's talk about the plan, the epistemology, what we want to do. That's the kind of question we need to ask. Okay, and well, how to do that? That's why I was so fascinated about the old Sharma paper, because he was one of the first people, let's say, who had this idea of computing the gravitational constant from the mass distribution of the universe. And I mean, we could talk 2 hours about all this and on the Machian stuff, but in remaining on the more general topic today, I would say, let's just say that's a valuable goal, and there are some interesting approaches, and so we might possibly someday hope for an explanation and a calculation of the gravitational constant. Whether you believe this peculiar approach is correct or not, let's leave aside. But okay, that's my argument. One day we should be able to compute the gravitational constant. But we have, if we talk generally about fundamental physics, we should set up a to-do list, what we need to do, and then with which methods we can approach this.
What are the steps that go into that? If you actually wanted to calculate the gravitational constant, do you mean by analyzing the mass distribution of the universe in general, like having this God's eye view of the location and density of matter throughout the universe?
I mean, the first step is always a coincidence. Okay, if in these revolutions or in these physical theories, even before Maxwell came out with a theory, so Weber and Kirchhoff had the flash of genius. Couldn't that be related? Couldn't could that be? And people, a skeptic would say, oh, that's numerology at the time. And then you need to have a very sound, mathematically well-founded theory that at the basis of that. I wouldn't say this theory exists, but clearly, of course, what exists is the coincidence, because you have the order of magnitude of the gravitational constants, 6.67 times 10 to the minus 11. And this is the same order of magnitude as c squared, the speed of light, times the radius of the universe, which is a measuring value. I mean, you measure the Hubble constant technically, but you know more or less what your horizon is, and divided by the mass of the universe, which is also a measuring value. It's with very high uncertainty, but as a matter of principle, you observe the universe, you observe the density of galaxies, density of stars, mass of stars, and so on. So you get here. So, and this order of magnitude coincidence is very, very remarkable. Yeah. First noted by, I think, Erwin Schrödinger in 1925. Even before Hubble came out with the concrete size of the universe, because you need the cosmological redshift and its interpretation to arrive at the size of the universe. And then only the coincidence, let's say, was available not earlier than 1929. But Schrödinger already suspected it in 1925, after the discovery of galaxies. He said, couldn't it be that the gravitational potential of the universe, which is g gravitational constant, times the sum over all masses divided by the respective radius, couldn't it be that this gravitational potential of the universe is equal to c squared, order of magnitude? Okay. which is basically the same idea. This is fantastic. I mean, this is really, I think, one of the most underappreciated ideas in modern physics. People see the point, but they call it with fancy, in my view, nonsensical names like flatness of the universe, or try to explain it with inflation forever. But it's not an explanation.
Can you explain why you would expect it to be equal to c squared?
No, well, the order of magnitude coincidence is there. So.
And then can you do some sort of dimensional analysis to understand what that big G is supposed to be telling us exactly? Do you know what I mean?
Yeah, I mean, dimensional analysis is indeed key. Is indeed key. It's not that difficult. I mean, before, I don't want to boast, but I mean, before I discovered the literature, I already arrived a little bit at the same formula, because all what you need to do is analyze the physical units of the gravitational constants, and you note these meters to the third power divided by seconds squared and kilograms, and then you say, okay, meters to the third power second squared, couldn't it be that there is already a c squared in it? Okay, that's very easy to detect. So you cancel that c squared out, but you end up with a meters over kilograms. Now, meters over kilograms does not make a lot of sense. But if you turn it around and you say, okay, kilogram over meters, that's mass over distance, that's a well-known quantity in physics. I mean, kind of obvious that this is the nucleus inside the formula of the gravitational potential. So, I mean, to be, as I said, I don't claim that this is the complete theory. I'm just saying that first we need to do that. We need to wonder about the origin, and this is a very intriguing coincidence. Okay, and then, of course, you have to start working. Do it the way Sharma does it with his potential, or do it the way Robert Dicke did it with variable speed of light. There are various approaches, and it's terribly difficult to find a technically satisfying version of that. I mean, that's part of what I'm doing. But I don't doubt that at the very end that something alike should exist. Okay, or at least if I'm mistaken, somebody else should come with a better explanation of. But please compute G, big G.
Inherently, it makes a lot of sense that if there is a constant of nature, that there would be some source for why it looks the way that it does. When we're talking about something like the density of the universe or the size of the universe, like let's say the size of the universe, there is a computation that's reasonable.
Mm-hmm.
But for density, we have an assumption that density is homogeneous.
Is what?
Homogeneous. Like there's the idea that wherever you go in the universe, it'll be roughly the same density. And it seems like they've been recently starting to find stuff that shows that isn't the case. I don't know if you saw this big ring that they found of galaxies that's, I think 3 billion light years across.
That's a very interesting discussion. And you're correctly remarking that it has been kind of a dogma, I would say, in conventional cosmology, saying that, well, on the large scale, it's isotropic and homogeneous, okay? And we know that, okay, it's basically an assumption. And if you really look closely at the mass distribution, it's not really evident. And there are very interesting results. I mean, there are lots of riddles which are called large structure. Large scale structure formation. How did the galaxies form? Why do you observe these huge voids? between galaxies. There's absolutely nothing in there, and very difficult to understand. And then there are people analyzing these structures, and some people have found even self-similar structure, like in fractals and in chaos theory, that you might well argue that this homogeneity is kind of unfounded assumption. We need to test it, and the evidence is not really clear. Nonetheless, I mean, if you look at the big picture, I would say that fractal structures aside, we have a well-defined horizon, okay? And you can compute as a matter of principle the mass which is included in that sphere. So regarding the computation, or the possible computation of the gravitational constant, it's a solvable problem. Yeah, I will say. I mean, maybe I will come back several times to that. The problem is solvable as a matter of principle, and you're right in holding me back and say, Alexander, I don't believe that, and it's true. I think we will come a couple of times to that point, but I want to tell the whole story about how can we possibly go ahead. Yeah.
Hey folks, this podcast is entirely listener supported. That means we have no sponsors, we have no external advertisers except for the ones YouTube pastes over this. And we've got nobody telling us what to do, and we really want to keep it that way. So please come over and give just a couple dollars a month over at patreon.com. Join our inner community, help steer the ship, and we will continue to advance the scientific revolution. Yeah, I think there's a lot of mysteries bound up in that. Have you, somebody once showed me that you could factor out not only c squared, but also the approximate rest mass of a hydrogen out of the gravitational constant too. I wonder if you've looked at that.
I wouldn't say figure out. So, I mean, I would, yeah, but you're correct. I mean, we should make a to-do list what we want to compute, and one thing is the gravitational constant, but there are several others. And where does all this bring us to? What's the final conclusion? My final point will be that all these discussion about constants and the implications will bring us to doubt at the concept of space and time. Okay, that's my final conclusion, but we have a kind of a long way to go there. So let's try to make a list of the fundamental constants. Let's start with the easy stuff, so to speak. The easy stuff, I mean, the brightest minds haven't done it for 100 years. So the fine structure constant, for example, it's the elementary charge squared over 2 epsilon naught at h and c. And the interesting thing here, it's dimensionless, so it's just a number, and it's, so to speak, it begs for it to be computed, but we haven't done it. Okay?
What is the significance of the fine structure constant? Like I've heard a lot of people referencing it, but I don't totally understand. I mean, big G, I understand. Fine structure constant, I don't understand as well.
Yeah, fine structure. I mean, the first interesting thing is that it is dimensionless. It's just a remarkable thing that you have various measurements, electrical constants, and so on, and you put that together, and you have a number. Yeah? And as Feynman phrased it, that's a magic number. God wrote it down, but we don't know how he pushed his pencil. And we know what kind of a dance we need to do experimentally to make that number come out, but we don't know how to put it into a computer, and the computer produces that number. Very abstract philosophically. That's just one interesting thing.
I think that specifically I was asking about the physical systems that it is relevant to.
Yes. I mean, it's the numerical value is is 1/137. Sometimes you may also refer to it just 137.036 and something. And technically it's the relation of two important velocities. The most important velocity in nature is, of course, the velocity as the speed of light. But then you have the most simple system, a hydrogen atom. What's the orbiting velocity? Well, in Bohr's model, if you assume velocities, but it makes sense. What's the velocity of the electron in the simplest ground state? And it's 1/137 of the speed of light. Okay, so you may phrase it that way. And then you discover it also historically. It was discovered when you explain the fine structure of the emission spectrum of hydrogen. So this line split up if you consider the various states, and technically you describe also this as that's where the name comes from. Arnold Sommerfeld phrased it, but I think more important is the relation of the electron's velocity in orbit to the speed of light. And philosophically, it's just remarkable that you have a number at all.
And it's interesting that the orbital velocity would be scaled in a way that relates to both the charge, so it might tell us something about what charge is, and it relates to the vacuum permittivity, right? That it might tell us something about what that means as well.
Can you elaborate on that? I don't totally follow.
Well, just if you look at the components that go into the fine structure constant, right?
Mm-hmm.
There's two other constants that we find there.
Hc, epsilon naught, and the elementary charge going. Well, I mean, elementary charge squared over epsilon naught is, whether you really want to look at it as two constants, it's something that always comes in a package, if you do electrodynamics, if you Coulomb's force, it's so it has the same unit as hc, and hc has the property divided by a length squared, and then you arrive at a force. So, what I want to say, I mean, yes, one important thing may be if you can see it that way, that the fine structure constant contains all of electrodynamics.
Mm-hmm.
Because if you have the electric force, you have always E squared over epsilon naught. And that's just the relation of that term to hc. Hc is, let's say, quantum physics, speed of light times Planck's constant. So if you have computed the fine structure constant, you know also how electrodynamics is related to quantum effects. That's, I would say, that would be a quantum electrodynamics that properly merits the name. Okay, because everyone is talking about quantum electrodynamics, but a proper quantum electrodynamics should compute that mysterious value that results from the relation of electric and quantum effects. Yeah, that's another important way to see it, I think.
Yeah, I guess what I'm getting at is that, what's the significance of orbital velocity for an electron? We don't really use the Bohr model anymore, but we have this sense that, at least from a chemical standpoint, that the electron represents the outer surface of the atom to some extent.
Yes.
And it's in some sort of motion. It has intrinsic momentum and so forth. There's something going on there. It's not this nice little orbital thing that Bohr imagined. It's some sort of angular motion. And that the energetics of that are coupled in a very clear-cut fashion to all of electrodynamics, and the emission of and absorption of light is really fascinating. It might tell us something about the mechanics of those processes at the end of the day.
Yeah, no, totally. There is even another aspect. I mean, it's very fundamental because it tells you about the number of possible atoms. because if you go to atoms with a higher charge, say helium, the velocity doubles. Okay, if you have two charges in your nucleus. So if you imagine an atom with a nucleus charged 137, which doesn't exist, so the electron on the inner orbit would have the speed of light. So that's impossible. You can't reach the speed of light or even go beyond. So 137 is a natural limit to the number of possible atoms in the universe. That's huge in a way, because all our chemistry depends on that. Imagine that number would be 5 instead of 137. What boring world would it be? Okay. That's I should be careful here, because that's the entrance door for some nonsense being told about, we have parallel universes, and maybe in the next universe it's 138, and the other universe it's 139. That's the explanation, and we live happily here because we're not number 5, and number 5 no life would exist, and because we exist, that's 137. No, sorry, that's
a good old
not the
anthropic
kind of explanation I like. Yeah, it's I still think that's our business to explain it. Yeah.
So it sounds like what you're saying is that the direction that physics should be moving into is figuring out how to compute these constants from first principles.
Yes.
How far along are we on that path? Is anyone doing that?
Can I ask an interceding question?
We have left the path. Yeah.
Before we keep going with this discussion of the progress of that project, I'm curious about if you have any skepticism about the true universality of these constants in the first place, because we spent an afternoon on the phone one time with Pierre-Marie and Stephen Crothers, and they were absolutely losing their minds about how unreasonable it was that Planck's constant was given this universal status when it was deduced in this very restricted context of black body radiation, which didn't really have any business being applied to gaseous atoms and so on and so forth. And if that was the case, then it wasn't actually a universal constant. It was just indicative of this one behavior in this idealized system of these soot-covered chambers. And the same might be said of, say, gravitation, where obviously things like the galaxy as a whole doesn't really obey the gravitational equation as it should, right? It doesn't rotate properly. And so people invent these dark matters and everything. I guess what I'm trying to say is there seems to be, ample skepticism about the universality of some of these constants in the first place. Where do you stand on that?
Yes. Well, Pierre is right about questioning this stuff about Kirchhoff's law, and then Planck used it based his derivation of his law of thermal radiation on Kirchhoff, and he's right in uncovering these mistakes that have been done. I'm not sure I fully agree with Pierre regarding the nature and significance of age. We had touched briefly the argument a little bit. And he is kind of saying that it's not universal, but then he said it was ubiquitous. And I frankly, I don't know really exactly where to draw the line. Think we could agree that it shows us a very strange behavior of nature, and it was unexpected, and it's certainly something very deep related to the microscopic nature of matter. I think we would agree on all that. And it's certainly not just around here on Earth or in our solar system and our galaxy, because if you look out at the universe, what you observe in analyzing quasar spectra, you see that fine structure there. So you see the fingerprints of these constant, I guess, in the distant universe. So I wouldn't really doubt that, even if you look at galaxies in 10 billion light years at a distance, I wouldn't doubt they have the same chemistry there of less than 137 atoms. So, I mean,
perhaps big G is a
I
bigger.
always welcome skepticism, but let's say that's a reasonable working hypothesis. No, one thing, however, what we should consider is that there was a very interesting speculation by George Gamow, who related the fine structure constant to the logarithm of Dirac's numbers. Now we have the next unexplained number in physics, the huge difference between first electric force and gravitational force. Just look at the hydrogen atom. You have the relation electrical interaction. You have the very, very weak gravitational interaction of the electron and the proton, but you have it. And the factor is 2.27 10 to the 39. Okay, so almost 40 digits. And this is a very, very huge number. And then, well, let's talk later about Dirac, what Dirac speculated about. But this is also one of these unexplained number nature provides us with. And we have to figure out, it's again our business to think about. And George Gamow said, couldn't it be that's the order of magnitude of the logarithm? Which in turn would imply that while the universe ages, and these 10 to the 40, the would be the number would be growing during the evolution of the universe. So also the fine structure constant, or in its verse, would technically grow very slowly. That would mean that maybe in the earlier periods of our cosmic evolution, it was 100, and then we had different atoms, or even it was 5, and we still didn't have atoms. That's, I think, that would be the really nice explanation from first principles, where you can say, oh, okay, we explained why we have this chemistry today, where we can form this all this biology. But that, of course, is speculation. Okay, clearly, but still, you need to do it. Yeah, whether you say, okay, it may be related to the age of the universe, or you come up with a ingenious idea about it's p to the third power divided by whatever smart combination of integers. I don't know.
Yeah, I've heard Pierre explain his objection to universalizing Planck's constant, but I don't have a solid enough grasp on the argument and its significance to be able to represent it in real time. And so, and I can tell that he thinks that it's really important to the way that we construct these relationships, but I haven't quite yet figured out, like, what is the implication?
It's a constant
like, if
of nature. It's a constant of nature, and it is significant. I don't think that anybody would really argue.
I think that his argument is that it could be different in other places.
I think in other material phases is his argument. God, this is going to be horrible.
So basically the idea is that the reason that it's the same in the white dwarf is because the material conditions that are producing that light are similar fundamentally to the material conditions of condensed matter in our own sun and in the black body. But if you were then trying to universalize it to, say, a gaseous phase of matter, that you would have a different relationship. Is that the...
Something like that, yeah.
We should put a pin in this until we can talk to
we'll have to get him back
forbidden
to
to speculate. It's very difficult to consider all these types of stars, and I myself working on Robitaille's model of figuring out or trying to make sense out of the density and how could it occur and how could that transition to liquid metallic hydrogen occur. But I also use age. I use the known physics, or if you want, the mainstream established physics at this point. Maybe I'm mistaken, but I think that's, at least for me, it's a reasonable working hypothesis. Yeah, I wouldn't. Planck's constant is not just in Planck's law. Planck's constant. What's the significance of it? Okay, it's a lot of places it appears. So first of all, in Planck's law. Planck considered it a technicality. He almost apologized for using it. It's an auxiliary quantity, he called it. That's why in German it's Hilfs, like where the H comes from. And then Einstein came along.
But let's be clear that's the one that's derived from the black body work.
Yes. Okay. And then Einstein came along and said, no, couldn't it be that we explain the photoelectric effect assuming packages of energy called quanta, famously. And that was this thought then attributed for the first time the real deep significance to Planck's constant. And then Niels Bohr, looking again at the physical units as you did before, said, okay, let's think about the unit in Einstein's famous formula, E equals hf, f being the frequency. So you have kilogram squared meters divided by seconds. And then Niels Bohr noted, oh, that's, by the way, the physical unit of an angular momentum. Couldn't it be that this is the angular momentum of the electron in the hydrogen atom? Wow, that was the beginning of quantum mechanics. Another revolution that, by the way, explained that the fundamental constants back then, Rydberg's constant.
So something like one wave of light, you get one kick of an electron that scales with this particular unit, which we call the charge and various things like this.
So, you can look at H as the strange property of light giving its energy in packages. You can look at it as the angular momentum, the intrinsic angular momentum of microscopic objects. And then you have other appearances. You have you have things like the Josephson junction and the Josephson effect, where it's related to cold temperatures. And then you have the van Klitzing, also another Nobel Prize, the Klitzing effect. It's called quantum Hall effect, and all these are manifestations of this strange quantum of action. Wherever you go to the microscopic world and you try to look at it, if you go to low temperatures, you always encounter that barrier to knowledge. I would call it. It's something very, very deep. And I would say that the very existence of Planck's constant poses one of the greatest riddles. Who ordered that? In 1900, people were happy. So is there an explanation from first principle why you can't do physics without that? And how would it look like if you don't have Planck's quantum?
Well, it seems to me, and maybe this is naive, but that if we go back to the example of Young's modulus is particular to the atomic structure of a material and the way that the atoms are bonded within it and the lattice and all of these physical things, right? You can say that they're not physical because we're going down into the quantum level at some point to talk about atomic bonding.
But you can learn a lot about the material system, essentially.
If you were to sit down and to ask the question, why does steel have a different Young's modulus than rubber, it would come down to the material properties of the lattice and the atoms within that. Okay.
Mm-hmm.
So is there a logical analogy that we can make to something like Planck's constant, that it is the material substance of nature that is giving rise to it?
Yeah, are we like somehow talking about the deformability of the electron shell? Is there, with respect to incoming light, is there some like material analogy that we can make this might be telling us about the universe?
Well, in a way, I would just say that space-time is not a run-of-the-mill material. It's not whatever material. It's something very, very fundamental. I mean, by the way, if you are able to compute Young's modulus, I'm sure from first principles that I'm sure H would be in there in the formula. No way that can do without.
I mean, I just look. I have like a really personal experience with this because my PhD essentially started with seeing a strange anomalous Young's modulus in a material and trying to make sense of why that was. And it was actually a biomaterial, and it had to do at the end of the day, which took us like 10 years to formulate this theory properly so that we could actually get it published, came down to the way that water was tensioned within this material under different chemical gradients, essentially different humidity gradients. And so we worked backwards from looking at this anomalous stiffness of this material that didn't make sense, right? These bacterial spores are, on the order, like they're as stiff as this table, which didn't really make sense, especially since they can expand and contract really easily. So we had to figure that out backwards, right? We had to put it through all of these different thermodynamic loops in order to see how it was behaving at different temperatures, in order to see the activation energy of the water within it and so forth. And so it was this process of starting with the constant and then perturbing the system in such a way that you could separate out what was going into making the constant the way that it was in a material sense and giving like a structural explanation for why it was the way that it appeared to be. And I'm wondering if we can't do something with the same thing with the atom and look at it and say, hey, look, the electron is the outer surface of the atom, at least for the chemists. It has some intrinsic momentum to it. That intrinsic momentum is imparted by light signals. And so what is physically happening to the atom during that? It seems like that information is enshrouded in that information to me. I don't know how we get at that answer, but it seems like that answer can be obtained.
Because without getting that answer, you have what to me seems like the biggest paradox in physics, which is that you go from field equations and vector potentials to matter. And that is a really nebulous gap for me, because if you start to ask about, okay, well, what is the atom made out of? You get that, okay, well, it's these particles, and then you start to ask, what is a particle? And a particle is not an object, it is an activity. And so if you have activities, then the question that you have to ask is, well, activity of what? And the answer is, well, it's just an activity, which is the fundamental unit of nature. And that to me seems to be the paradox.
Except it seems like the chemists have this figured out, as far as I can tell. Like the chemists understand the electron being the outer surface of the atom.
Sure, but I mean, even the chemists, like you ask them, like, what is it? And they'll revert to the particle explanation, which is that...
Or the Bohr model or something, if they start moving the electrons around.
Right, like you still see these like little bowling balls, but when you really start to ask a particle physicist, like, well, what is a particle? It's not like they have an object that they can point to where they're like, okay, well, there's this little bowling ball and that bowling ball is the electron. It's like, it's an activity, and it's an activity in the quantum field, and somehow that activity in the quantum field that is immaterial on the most fundamental level transitions to being material when you cross a certain size threshold. Yeah. And I'm like, doesn't it make more sense to think of it as an activity in a material? Like after our dislocations in the ether conversation, it just seems more and more that I'm like, okay, well, if we understood the material properties of what is being dislocated to produce these signals, then perhaps we can start to tease apart the various sources for the constants.
Okay. Just a moment. What Sheila said about materials. I risk here to say stupid things, I guess, in material science. And as we said before, I mean, water already is very complicated. We're not able to compute the boiling point. So a lot of things on top, which I would say are due to the complexity of the matter, already we do not understand. I wouldn't necessarily venture the prediction that H is really responsible for anomalies showing up there. On the other hand, of course, I mean, if you construct nature differently, different H, it would certainly affect everything. And what you're saying about,
Well, I'm not. Can I be clear?
how-
Like, I'm not saying that H should be involved in this water calculation or anything. I'm just saying, like, as a model for how I learned how to do physics, was hey, you have you have some interesting measurement that you make, whether it's H bar or the Young's modulus of this bacterial spore system I was looking at. The next step is basically saying, why is this happening? Why does it have this property? And then giving a material explanation for the actors involved and how they conspire to give it this particular character, this quality, this quantity. That I'm just using it as an analogous system. You know?
Yeah. I mean, we all try to make sense of, and working with analogies is very helpful. And we talked about this about when we were discussing the ether and what might possibly be a particle. I think that it's a little bit a different angle viewing the problem. I would say that the very existence of H just sheds light on the problem that we get if we go to the microscopic world, that it doesn't work like ping pong balls in our ordinary imagination of particles. It's something very, very different. Not only the concept of a particle, not only the concept of a mass, and even more scaring, I would say might be even something wrong with space and time. But okay, we're still here. I was anticipating a little bit that since we're talking about the Planck's constant, but that doesn't harm. Well, I mean, at the very end, I think Planck's constant is one of the most important, maybe together with C, the most important fundamental constant, because as a matter of principle, it cannot be explained the way possibly the gravitational constant can't be explained, or the way epsilon naught and mu naught together with C could be explained. You know?
Why?
Getting back to that very general discussion about how can we achieve revolutions, what can be computed. Let's make a list of all the gods of modernity, of all the constants, and then discuss what can be resolved and where is a problem as a matter of principle. H bar is one of the constants where there's a problem as a matter of principle. But if you don't mind, we can just at least mention briefly the other constants.
Yeah, and then let's come back to why H bar is such a problem.
Yeah.
Okay.
Oh, just another sideline before. I mean, all this discussion about constants, I think it's a little bit in the subconscious of physicists, because very rarely you find literature, and even it played a very important role in what physicists believe that is important for physics. And I want to show you this book, Einstein. Ilse Rosenthal Schneider. She was a doctoral student in Berlin in the 1920s, and after World War II, she then started an exchange of letters from Australia with Max Planck, with Max von Laue, and also Einstein. And yeah, very, very smart questions. She was, I mean, really bringing Einstein to that point of expressing his views about fundamental constants of how does he see that as a problem, and then that's only for that reason we have this documented that Einstein said, oh, I don't believe that any reasonable theory of physics can contain a number the creator invented just because it was in his mood. Okay, I don't believe that, and that's okay. Going back to gods of modernity, we don't accept that. So Ilse Rosenthal was really, I really like that. Yeah, certainly a soulmate of you, Anastasia. Questions? So what about the list of constants we can consider? Another Einstein quote in this respect. He said that what he said, even the even the what did he say? Something about iron. Even the density of iron or the mass of an electron is something we should explain. He didn't say that literally, but in context, okay? He said, let's not be happy with just measuring these things. There must be a fundamental reason. Once we can think about an explanation, let's strive to understand this. So we definitely need to worry about or to also ask for explanations for the size and the mass of elementary particles. Okay? These are measuring values. There's no debate about that we have a radius of the proton, which is 0.84 10 to the minus 15 meters. Okay, depending a little bit how you measure it, but okay, it's a measuring value. And you need to explain that, why it's not 10 times of that. And then you have the mass of the proton. It's also something left to explain. Then you have...
Well, mass here is also, it does some work because its mass is reported in electron volts.
Well, that's a technicality. You transform it by Einstein's E equals mc squared, and then that's the energy, and you can express it in electron volts. But I would say it's just the mass of a proton is just 1.67 times to the 10 to the minus 27 kilograms. Okay, that's
it's like a mass equivalent. It's a mass equivalent.
Yeah, it's okay. All right.
Yeah, the concept of mass is originally defined in terms of gravitational
systems. 1 mega
systems.
electron volt would be roughly 1 mega electron volt.
Yeah, but I think Unizicker is just bringing up the point that mass is originally defined in terms of gravitational systems. But I'm not sure where you're going with that exactly.
Sorry, not mega.
I think
1
that
giga electron volt. Okay.
I think that the place where I was going with it is still this idea that it is an activity rather than an object. And so it's...
You got to be really careful with that word, because to most mathematical physics, objects can be sets of data as well.
It's an
I got
activity...
lost for like 3 hours with my advisor about this one time.
Activity
go with
versus
Newton's language.
Body.
Yeah.
Right? So it's hard for...
I would also struggle with the definition. What do you mean by activity? So...
just there's a time variable inherent in it, right? So something with intrinsic momentum specifies motion. And like a body, like a material body in the Newtonian sense, doesn't have intrinsic motion to it. It's just a static concept, right? It's defined by its surfaces. It's not really defined by its motion. So it doesn't have to be in motion to be defined. I think that's the definition.
And when it comes to figuring out these fundamental questions, like why does the proton measure the way that it does? If we confuse it as being a static body versus an activity inside of something,
an activity of some other sub-bodies.
No, I mean,
right? Because it's like if you have
I'm not taking parts here. I'm not.
Sure.
I'm not suggesting this is something static. I mean, just you can reasonably assign a mass, or if you want an energy, assign an energy. Doesn't matter. I mean, certainly. It's not something static because we have quantum mechanics. Microscopic objects behave like waves. So the idea would be it's probably something more like to a
like a tornado or
circular light wave or de Broglie waves or something like that. How do you describe it? I certainly don't imagine as a static particle you can go around and watch, and no.
I didn't mean to derail you. Yeah. So, but basically, you were basically going through the list.
I mean, this is if you want. We have 3 stages of scientific progress, and as I say, the first stage is idea, coincidence. Oh, that's intriguing. There could be something. And then, of course, you need that very tedious technical work. Develop Maxwell equations, okay? Develop quantum mechanics and Hilbert spaces and the Schrödinger equation. Just do it in a minute. It's not that easy. But you need all that to justify the idea. And then at the very end, you are rewarded with a less with one fundamental constant less. But it's a huge progress. And if we try to discuss all these technicalities that then eventually may lead us to a theory, and you use fields and vector potentials and Lagrangians and so on and so on. But that's, I mean, we would need weeks to discuss all possible ideas here. I know it's kind of, well, kind of a poor approach, but I would like to remain at the first stage, at just pointing to these intriguing coincidences that might then provide us with motivation to go into theories. Yeah,
that makes sense. I mean, but I derailed you. You were going through this list of the constants.
No problem. Well, I mean, we have covered almost, I think, one half of the constant. We had defined structure constant. We had Planck's constant. We had the gravitational constant. We have, of course, this. Let's later the speed of light. But then, of course, you have the proton-electron mass ratio, which is 1,836.15 something. And Dirac pondered all his life about this number. He wanted to figure out, to calculate it. No way. He failed. And nowadays nobody seems to care because, well, okay, it could be it's too difficult, but please don't take it off from the agenda. It's still your business as a theoretical physicist to make sense out of that number. I'm not proposing anything particular. I don't have a good idea. I just would say in that case, well, okay, as a matter of principle, is some genius comes up relating it then to defined structure constant, to pi, to whatever, would be possible as a matter of principle. Okay, would be very nice. Yeah, eventually understand nuclear physics and so on. So this is one number. And then, as I said, you have the mass of and the size of the proton, which I take, when I say proton, I really mean here the maybe only fundamental particle. Okay, because it's the only stable one. Of course, you have also the electron, but you already have the ratio of the mass, and the electron has no measurable size. So you necessarily consider the proton as the biggest riddle. That's the real thing to explain. And you know from my other discussions and my critics that I don't really believe in that quarks or all that fancy stuff really brings us ahead in fundamental physics. So once we at least say, let's focus on understanding the proton properly. Once we have understood, then we can discuss anything else. But that's the
do you have a sense of how the radius is calculated or measured for the proton? Is that from X-ray diffraction, or how is this done?
I am not in the technicalities, but I think it's deviations of spectral lines. You have the usual hydrogen atom, and then you have an hydrogen atom with a muon instead of an electron, which is 206 times heavier than the electron. That means it must be much closer if it has the Planck's constant as an orbital momentum. And being much closer, it's also much closer to the charge distribution of the proton. And by looking at the difference of the spectral lines of the usual hydrogen and the muonium, then you can do a series of calculations I'm not familiar with, but that's the way how they determine the charge radius of the proton. Yeah, but let's say it's a measuring value, or even more simpler, go back to Rutherford's experiments in 1914. He didn't use protons, but he used alpha particles, helium nuclei, and that's basically 4 protons. Though, as an order of magnitude, the size of a helium of an alpha particle is already in the same order of magnitude as the radius of the proton. So it's a measuring value at the very end, something you have here, about 10 to the minus 15 meters. This is the microscopic world, And nature provides us also with messages, I would call it, but these are constants of nature in a very general way. You have the mass of the universe and you have the size of the universe. And then there are two very interesting, I think, very deep coincidences, first mentioned by Dirac. I said before that Dirac noticed that the ratio of the electric and the gravitational force in the hydrogen atom was a number with 40 digits. And he pondered also part of his life about that number. How could I possibly find out? And he was kind of hopeless because he said, that's just too large. I don't have an idea. Get help, but it's nothing for me. And then when Hubble at the end of the 1920s discovered the size of the universe, for the first time you could have a measure of the universe, he said, wow, the size of the universe divided by the size of the proton is also a number with 40 digits. That's not just coincidence. There must be a reason. That was Dirac's argument. And of course, that's called Dirac's large number hypothesis. And people are saying, okay, that's numerology. Who knows? I don't believe that. Yeah, but sorry. This kind of numerology that led us to Maxwell equations via the speculation by Weber and Kirchhoff. And that kind of numerology was at the beginning of when Johann Jakob Balmer figured out the spectral lines law of the hydrogen atoms. So you need these kind of intriguing coincidences to get started. Okay.
The question becomes, what does this actually mean, I suppose? Because with respect to the size of the universe, it seems to me that most astronomers, when they talk about the size of the universe, they mean as far as we can see, something like that. And I wonder if what this isn't telling us is something more about the extinction of light at a distance. It's a possibility.
It's a little bit more. It's more precise than as far as we can see. Of course, you have this limit of distant galaxies and distant quasars, but technically you determine the Hubble constant. You see it's quite easy to the redshift, and that's another sideline. Whether redshift really means real expansion or not, that's another question. But also, if you think about alternative cosmologies, the universe is not static; it has an evolution. So you were able, by measuring that Hubble constant, you can measure the age of the universe. You multiply by the speed of light, and you have a reasonable horizon. Okay. So that's a measuring value, and it sounds very outlandish. I saw it from your reaction, and it's true. When I heard it for the first time, you say, "What?"
It's just like you say, it's a measured value, but it's predicated on theory, right? It's predicated on this idea that the universe has a beginning, and that the redshift is telling us about that moments of the beginning and so forth. From an empirical standpoint, all we have is as far as distance is concerned, is how far away, using some standard candles, that the edge of the visible universe is.
Yeah. Well, that's however, one thing I'm it's strange for me, but I'm in line with the mainstream in the sense that I'm not a steady state adherent. I think Big Bang is a wrong picture because we may not have material expansion, but we still have the spreading of light, because light spreads. It's just, you cannot imagine light not spreading. That's the very definition of light. So, and what you see also, I would argue, you see the redshift. So there is a evolution, clearly. And yes, there is a kind of a beginning of the universe, whatever complication you may add with different time scales and length scales and so on. But I would argue that you have that. I mean, otherwise, of course, you're right. It wouldn't make sense to assume a horizon. But then, if you have or if you don't have a horizon, then you don't have masses included in your horizon. So forget about computing the gravitational constant. So
maybe, because I
it's
think
okay,
but I think that even if you, let's say that there isn't a Big Bang and there isn't this sort of like expansion from a central point, I've always thought about it in terms of the transmission of light, and the limit of transmission of light is also the limit to the transmission of influence.
Yeah, with gravity as well. They both fall off with an inverse square, right? That
Mhm.
I mean, it's still, I'm sure this relationship is important in telling us something, but the metaphysical underpinnings of it are going to really inform which direction you take the theory in, right? So if you say that the universe has a beginning, and I say, well, no one's ever given me a good mechanism for a beginning of existence, so it's hard for me to entertain that idea. And so then I'm looking outside of that, and I'm thinking, okay, well, this is where the inverse square law falls off to essentially something approaching an asymptote, where the influence or the light or whatever is just petered out, essentially. And so that might still be really interesting with respect to the proton and the way that the atom is functioning during the generation of light and so forth.
I actually think that it becomes more interesting, because if it is not a question of the Big Bang and expansion and, this kind of nebulous idea of the space itself expanding, and then all of a sudden you have, okay, well, light must follow some kind of material path from the farthest regions of the universe to where it reaches us. That means that there is a sphere of influence that is materially defined as a product of speed of light in the medium. And I know that's like very etheric, and I know that there's all sorts of problems with tired light theories, but I think that there is reason to believe, like, do you know the work of Carver Mead?
Not really in detail, even if I've interviewed him. But yeah, he's also into variable speed of light. He has also done work there. Yeah.
And he's really into simplifying concepts.
Okay, but maybe it's a sideline. Well, it's an important one. I mean, you can doubt the Big Bang, and I'm a skeptic of Big Bang cosmology. But on the other hand, I mean, the reason for why there are two hostile communities so fighting to each other and throwing the respective contradictions to the other side. Don't you see that this is a contradiction? Don't you see that that is a contradiction? I think that both are wrong. And what I think is, I mean, this variable speed of light cosmology provides a reasonable explanation for both possibly resolving the contradictions of the conventional Big Bang, taking away the epistemological absurdities such as how did it came into existence, and so on. And on the other hand, respecting the evidence we have that the cosmos is not static. I think there is evidence. So, and it resolves also a little bit, at least, the arbitrariness of what you say, okay, it started at a certain time. I mean, who set the clock? Huh? That was your objection. Because if you have variable speed of time...
My objection is just the mechanism. Like, I just don't see how... like, in physics, you have to explain how the material bodies are interacting.
Yeah, but it's much less of arbitrary mechanism you need there. Because you don't have to wonder about the beginning of time, because back then you had much elevated speed of light and time running much faster. So you still, if you count in local time scales, the universe is still infinitely old, So you have kind of resolved that, or even maybe smoothed that epistemological absurdity of the Big Bang. However, well, I mean, I could praise all this variable speed of light cosmology, but maybe for right now, I mean, just
Do not forget to get your tickets to Demysticon 2024. We are gathering in Austin, Texas on April 7th and 8th for 2 days of talks, conversations, workshops. We're going to hang out in the evenings and just talk about the things that are most interesting to us on the scientific frontiers. Tickets are for sale right up here, and we hope to see you there. I don't think that there's a real issue with dealing with redshifted light telling us something about the boundaries of the universe, whether that's the size of the universe, full stop, period at the end of the sentence, or the size of the sphere of influence and contact that we have with the sum total of material. Like, I think that those are two metaphysically different ways of interpreting the same results. And I think that you can get back to the question of why is there relationship between this distance and the size of the hydrogen. Like, those are both of those things will tell you something. And I think that what Shiloh's trying to get at is he's like, it might make more sense to look at it from this interaction, like materialistic sense, because if the hydrogen is made of the same stuff that is also responsible for the transmission of light, then there's something about the substance that is the medium. Like I talk about this and it sounds like I'm talking, ether, but if light requires some kind of connection between atoms in order to be sensed, which is kind of what Carver is on about, right? Carver's like, look, you light is a communication.
Well, it's either that or magic. I mean, right? It's either physics or it's magic. It's kind of this. You can call it the ether or whatever you want, but somehow the atoms are affecting one another. And if I want to affect something in this room, I'm not just going to magically like cause the desk over there to flip over. I have to walk over and flip the desk over, right? So we can talk around it all we want, but something's going on.
And so I think that the puzzles here, these questions of, like Dirac spends his life wondering about like why these relationships exist. I think that he's informed deeply by the quantum strangeness, where things happen without a real sense of why they could be happening. Because it's like Einstein references the non-kinematic ether of space-time. And so he recognizes that there must be a network. It's in his Leiden address. And so he recognizes that there must be a network. And I puzzled for a long time. I'm like, what did he mean about non-kinematic ether? And I realized that I think that what he's saying is that it is so permissive of a substance that it allows things to move through it without being able to really affect the source of the motion.
Yes.
And so if Dirac had been thinking about it in a more material sense, then maybe he would have been able to resolve the conundrum. Because I think that it's really, really hard for brains, even the best mathematical brains, to think about very difficult and large mathematical operations without having a visual model. Like when we talk about understanding things, we talk about...
Einstein was very intuitive, yes. But I agree, yeah. Yeah, but we're still at the technical difficulties. But before, I mean, you have to be convinced that your basic idea, your intriguing coincidence is correct or worth, let's say, spending time on it. And you were very skeptical. I saw it in your expression when I told you about Michael, your relation of the forces. How should it be related to the size of the universe? That sounds kind of absurd, but hold on. That's just one coincidence. And but if you have another coincidence that's kind of a quadratic, improbability that this is just coincidence. So we have another observation of Dirac, and he says, okay, let's observe the mass of the universe divided by the mass of the proton, or phrase it a different way, the number of particles in the universe, and that's 10 to the 80. The square of that magic number 10 to the 40. And this is another independent coincidence, because you could easily make, say, the protons 1 million times heavier and have at the same time 1 million times less particles in the universe. Why not? Anything else would be the same, right? But still you have these two coincidences. So, and I think there is a better way of phrasing Dirac's first coincidence, because if you phrase it like the relation of the forces to the size of the universe, it really sounds outlandish. But you can do, a relatively easy calculation, assuming that you have computed numbers like 137 and the proton electron mass ratio. And then you can show that this first relation, because it involves E squared, the electric force, it involves H, and it involves the gravitational constant. And if you all transform this, it boils down to a much simpler coincidence, which is Planck's constant is approximately the product of speed of light, c, times the radius of the proton times the mass of the proton. Wow. Can even add p over 2, and then it's very precise, almost in the percent level. But that's a very intriguing thing. And once in a while, you find papers on the internet that rediscover this. I have discovered this relation, and no, that's Dirac. That's just another, and I guess more intuitive form. And we really have to wonder about. It's really something exceptional. Why is Planck's constant approximately equal to the speed of light, the mass of the proton, and the radius of the proton? And by the way, that's the only, the proton, that's why I consider
for me, it's just like
the important particle. It's the only particle, the only stable, massive particle, and it's the only one for which that peculiar coincidence holds.
If we map it all the way back to the fine structure constant and try to pick out Planck's constant from this relationship, it seems like it's telling us something about the electron's material interactions with the proton. Like there's some there's some information there about what the electron is with respect to the proton. What is happening there between those two? That's what it seems like to me.
Is there...
Mm-hmm.
Oh, no, go ahead.
Yeah, that's the huge problem, let's say, still open. That's what we have to do. We need a theory, but just, you need, I would just, on this first level of discovery, so you need to compute 1836. Do that and you will gain some insight. You would certainly understand more once we have this. We don't have it, but as a matter of principle, then we would possibly gain insight to the relation of the proton and the electron and the structure of the nucleus and so on. Yeah. You need a whole package.
There's a big elephant in the room.
I'm describing kind of 7-8 steps, and each of them would be a major revolution in physics, similar to quantum mechanics with the computation of Rydberg's constants, similar to Maxwell electrodynamics with the other equation, and so on. Yeah, but we have a lot of unknown stuff. There's a lot of work to be done, unfortunately.
I think framing the problem structurally is really interesting. It's because the chemists have done a great job of showing these electron orbitals and how the electron energy gives rise to these harmonic shapes. Like you actually can start to imagine, like I keep saying over and over again, the electron is the outer surface of the atom. But the proton is like in its own universe, like it's somehow connected to the electron. It has interactions at a distance somehow. That's probably not magic. Like there's probably some physical interaction going on there. And I think by tearing apart these relationships, we might get closer to understanding that interaction in a physical, material sense.
Mm-hmm. Yeah, in a way, you're right. Mentioning chemistry, we have. I mean, atomic theory is a fantastic achievement, and we can really say to a certain point, we have understood the atom with quantum mechanics. I mean, you compute all these spectral lines of the hydrogen and also of others. It becomes complicated, but okay, as a matter of principles, we are there. That's fantastic. We have not achieved the same level of theory quality in nuclear physics because you just don't have the respective formulas for the resonances of the nuclei. There are lots of data, lots of isotopes. I'm hoping that's one of the first things maybe artificial intelligence could tackle, get all the data of the isotopes and try to make sense of. But it's really difficult. It's not solved. I mean, I don't want to offend the nuclear physicists, but I already offend a lot of people. But it's a mess theoretically, you know. They haven't done the computation. There is some fancy imagination about shells, and even the Nobel Prize handed out for that. But at the very end, it's not really solid ground. You don't calculate all these resonances of the isotopes. No way.
What, is it just too difficult of a calculation, or we don't understand the way that they're related to one another? Like, what makes this so difficult?
Well, as a matter of fact, a lot of smart people have tried it without success. So I guess, yes, I mean, always start with the fundamentals. I mean, I wouldn't go to try to compute the resonance of an iron atom, because I would say let's just understand the proton first. And certainly, once you have understood this 1836, once you have computed that number, then you can go ahead. Whether this is done with nuclear electrons or something else, or I mean, Niels Bohr said that he contended that nuclear physics, for true understanding of nuclear physics, he said there will be a similar revolution will be needed than quantum mechanics.
I mean, it makes sense. It makes sense that it would be lagging in some sense, just because the electron is on its, well, distance-wise, let's say spatially, it's much bigger. It's much easier to look at how it's interacting between atoms. Like the chemists deduced a lot, right?
Yeah.
So you can see, you can kind of cross-correlate these macro-scale behaviors with your theoretical behaviors. You also have light, which is really nice.
Yes.
Right? And all of these things are kind of lacking down at the level of the nucleus. It's just a much tinier, more obfuscated system that's more difficult to penetrate.
Exactly. Yes, from a practical point of view, it's much less accessible. You can produce all kinds of light. It's also visible light. What a nice coincidence that we were able to discover that. You don't have eyes with X-rays. And if you look with a microscope, that's a factor of 100,000. I mean, 5 orders of magnitude, it's not nothing. And an atom is already small here. Okay. So the nucleus is something really, I would say it's still mysterious. There are a lot of discover. I don't think, that's why I'm also skeptic of quarks or even the concept of strong force. I think all this is misleading stuff that will not bring us to a fundamental level of understanding. You need to compute 1836. That's the starting point.
Yeah, I mean, so just to clarify, so 1836 is the dimensionless physical constant that gives the ratio of proton to electron mass.
Mass, yes, exactly.
So
not an integer, point something, yeah.
Yeah. So with the things smaller than a proton being less significant, I think I inherently agree with you, because I feel like if there is a material substance that is the source of the measurement, so you measure a proton and there is some kind of stable motion of that substance, and that is what always gives you the motion and the size and the apparent behavior of the proton, it makes sense that if it's some kind of stable conformation, that if you break it, you're going to get other activities that radiate outwards from it that are also, they're just the products of the explosion. And so if you break something that moves in a specific way, in a concise, coherent way, you'll always get the same explosion. But what you're really measuring is you're measuring the ability of that substance to deform when you put enough energy into it at the location where there is a proton to cause this stuff to move out from it. That's kind of how I see it.
Yeah, not sure. Well, I mean, you just don't break it up, the proton, you know. And certainly you cannot divide it into parts. So what you can do is, of course, doing high energy experiments and then smash it, and a whole lot of other stuff can be produced, always in particle antiparticle matter. That's also an interesting sideline. I mean, this concept of particles and antiparticles, why and how is it related to the direction of time? Yeah, but what you need is a mechanism. You need, I think, really you need a model of the proton. Is it total speculation, but is it a circular light wave? I mean, would add up a little bit if you do the numbers. You have the circular light wave would have an angular momentum related to h bar, of course, and then you have speed of light times the mass times the radius. That fits more or less. So I think this this coincidence of Planck's constant more or less equals c times mass of the proton, radius of the proton, tells us something. It's certainly intriguing. It's very neglected in contemporary physics, and it's the much more interesting form of Dirac's first large number hypothesis. You can transform that. I did a video on that, and that's called Dirac's Way to Quantum Gravity and Why Anything Else is Crap. Because
Nice.
being a little provocative, I mean, everybody talks about quantum gravity, but what is quantum gravity? Physics is a quantitative science. Come out with a number, please. So don't talk about concepts and this and that. Compute that number, and whether you believe it or not, you can be skeptical about the number. But
I was only skeptical of I wasn't even skeptical. Don't misunderstand. I wasn't even skeptical. I was just that
That's just
phrase,
what his face looks like.
That phrase, the size of the universe, requires a discussion by itself. That's all I was responding to. If you saw something, it's a very loaded concept, right? It requires some metaphysical underpinnings, and there's bifurcation points in the way you interpret that data.
Yeah, but maybe you can start liking it a little bit more if you realize that it's actually it could be a potential key to address this very fundamental problem of quantum gravity, how to unify. I mean, what would that mean? Unification of gravity and quantum is something like computing the ratio of the electric and the gravitational force. Okay, equated here electric and quantum force. I said that you need to compute also 137, which would be the unification of electricity and quantum behavior. But once you have done that, you can unify the quantum with gravity, and then you have this number computed. And Dirac was it's just the only idea around how to access this problem in a quantitative manner. Huh? That's where I would say that's the only game in town, as string theorists love to state. String theory is the only game in town. No, Dirac's idea is the only quantitative idea in that direction. Anything else is literature, poems. Yeah.
To close, I wonder if we can't talk a little bit about what you were saying, problems with space-time, because it seems like we've
we're
come
already,
to this place.
We're already very close here. I said I think we have covered already all the list of constants, which are the two numbers: gravitational constant, Planck's constant, speed of light, mass and size of the universe, mass and size of the proton, and then you need a lot of equations to solve all that. There's one important thing, preliminary. You need to get rid of this unit of kilograms. That's kind of, we need to understand the nature of mass, but you would like to have a formula, say a model of the proton, just with an input of speed of light and radius, and say, okay, in the vicinity, this protons creates a gravitational attraction, finds mass, this and that, and then you have the theory, but you don't need that specific definition of kilograms any longer. You don't want that anymore, because it's an arbitrary element that has been inserted into physics. Okay, so from a fundamental point, you need to eliminate also that, and then you end up with just two remaining constants, which are not explainable as a matter of principle. You can remove the unit of kilograms, and that would lead to Planck's constant having the unit meters times second, and speed of light, of course, meters per second. So you have two constants left, unexplainable, no possible thinkable formula that you can derive this, because there are no other constants of nature left you can put in a formula. You have just these two with units meters and seconds. Okay? And I think the very existence of these two constants points to a problem with space and time, measured in meters and seconds. Because space and time are, at the very beginning, our first, if you want, arbitrary assumptions about physics. That's how the entire story started. I mean, of course, it's kind of scary, because you have to knock at Newton's door and say, "Oh, think about you. You still want to postulate space and time." But that might be at the very beginning of the problem.
Unpack that a little bit. I don't quite see it yet.
Okay, so I'm but you understood the concept. I want to explain physical constants. I didn't say how to solve it, but as a matter of principle, you can eliminate this. You can find an ingenious theory that realizes Dirac's large number hypothesis. You can calculate the Fein structure constant. You can calculate the gravitational constant and so on, but still you have h and c, Planck's constant and the speed of light. What do you do with that? Okay, there must be a reason for the existence. Think in the mindset of a mathematician who has only numbers. I want to describe reality. Now the physicist comes along and says, here's two gods, C and H. You have to believe that. You need that. I was like, why? Why do I need that? Yeah, why? Yeah. You postulated space and time. Space is measured in meters, time is measured in seconds. And once you postulate that, you need that kind of arbitrary postulates to do physics. But that might be the very root of the problem.
Why are they arbitrary postulates? Inherently, they don't seem arbitrary.
Space and time?
Yeah. Because, I mean, they seem like they are, like, space in terms of meters is, the distance between me and something else. And
or a way of like measuring the length, or like the size, let's say, of some material body, and then time is just how things change, right? So we recognize that the world is dynamic.
Right. I mean, it seems very, very clear to you, and obviously, I mean, it's two concepts most people haven't reflected about, because it's so clear, so obvious. I mean, seemingly you can't do physics without stating, okay, there is time, there is space. But the fundamental question is, indeed, why do we have that strange 3 plus 1 dimensional structure and not another structure? That's something left to explain. And Newton's postulate is a postulate. I mean, it makes a lot of sense, and it's terribly successful, wonderful, and no debate about that. But not necessarily it's the most fundamental description of reality.
Can you give me a hint of how you would be more fundamental than describing something this way? Like, how could you imagine simplifying reality beyond
distance and cycles
and motion?
Well, I mean, you can think about mathematics, you can think about mathematical structures, but before that, I would just invite you and think about as C and H as anomalies. Anomalies in the sense of Thomas Kuhn, philosopher of science. You have showing up something unexplained. You didn't expect that. You don't want that. It disturbs you. It shreds your theory. That's what H did with classical physics. And even C was a problem. I mean, C had an interesting history. It was first the astronomical curiosity. Okay. Oh, Newton thought the speed of light would be infinite. No, it's finite. Yeah, why? It's finite. Now, this is a question. You got to answer that. I mean, the Newton's idea, fantastic derivation of mathematics, also counts its velocity, acceleration. But tell me, why should there a speed limit in our physical universe that prohibits you from accelerating beyond the speed of light? Who needs that?
But in all materials, there's a speed limit for deformation,
right?
Right?
But you're a material scientist, but you work on top on that. I mean, you're already on that stage set by Newton with, of course, believing in space and time and materials, but and then you have the speed limit. I don't deny this is interesting and very interesting analogies. Okay, we agreed on that our last talk. Okay, but at a fundamental level, or let's say from Newtonian mechanics, there is no reason whatsoever for the existence of C. You don't need that. It's a nuisance.
Well, Newtonian mechanics is famously mediatorless, right?
Is famously?
Mediatorless. Like, he didn't have a mediator for gravity. And it tortured him for his entire life.
It's like not even really mechanics. I mean, I don't think that's the fair word to.
It's mathematics. This is
a description of reality, right? But it's not mechanical in its nature. It's not like Newton provided a mechanical explanation for gravity or something, right? Or light, for that matter. He tried with these little these bullets of light and so forth. But
and I think that this is a really, really, really important metaphysical fracture. That actually there's a schism in the way that we think about nature. And on one hand is that when you boil down to the bottom, there is mathematics. And on the other hand, there is material. And so the question is, what is primary? Is
material in motion.
Material in motion. Like,
I would question that. I would question even the concept of material. I mean, from a really philosophical point of view, I would argue that it would be desirable if you just use math and nothing else to describe the reality around you.
But the math has to come from
why?
somewhere. Because the reason that I don't like this, the reason that I don't like
me any longer.
No, we love
Get
you.
out. No. So check it out. I think that the thing that leads me to is that we live in a simulated universe. Like, if at the bottom is math, if I was inside of a computer program and I got down to the very bottom of the level that was accessible to me, and it was just algorithms. Like, I had access to the code, and I could read the code, and the code had all these constants in it where somebody set out that, like, okay, so this is the size of the proton, this is the size of the electron, this is their ratio. And I find just these mathematical operations, I have no other possible recourse than to say that I live inside of a computer.
Well, I don't want to really get into that debate about the matrix and that, but I mean, I would say there's still two different things. Simulation would be something digital, would be integers, and math is a lot more richer than that. You have, well, but of course, I mean, of course, I mean, you can argue that you don't like it, but on the other hand, I would retort, so you believe in the gods, C and H.
I just think they signify the material properties of the substance that's being deformed to give rise to all the phenomena that's apparent.
Yeah.
Where I'm like, there's stuff, and the stuff is in motion. And obviously it has to be something different than things that are made out of atoms, because we're talking about something that the atoms are made out of.
Yeah.
But
you want to start without any arbitrary assumption. Also, the idea of a material, remind you, I mean, if I want to explain the proton, if I want to have a model of the proton that works, that just based on, okay, C and the radius of the proton, but it should explain everything without the idea of what is a material. I mean, we talked about could be a topological defect of spacetime, but that's a mathematical entity. Okay, you have a classification of topological defects. You can describe it with homotopy groups, but I don't want these kilograms. I want math at this point.
Kilograms the fundamental concept of mass arises from gravitational tension, right? So these are atoms pulling on each other through some connectivity. At least from just first principles, like you can't get tension without pulling on somebody. That's how you get it across some structure. And so you're just scaling tension.
It's kind of dangerous to bring in all these ideas, conventional ideas that formed in our mind. Of course, I mean, we were successful in describing reality with this picture, but it's worth pondering what is a successful model or a concept we have developed in our minds, such as space, time, and matter, and what is really necessarily the most appropriate description of reality. And I would just invite to ponder about that. And if you look at it, that C is really an anomaly of Newtonian physics. Newton did not know about the existence. Then later, it turned out that it was really significant, because also not only light had the speed of light, but also matter wasn't able to be accelerated. There was also a speed limit for matter. And then you can see Einstein's special theory of relativity as working around that problem. But even Einstein did not explain the very existence of C. I mean, he very elegantly made out a theory and fixed, so to speak, the problem that Newtonian mechanics got with the discovery of these relativistic effects. But eventually it was a bug fix paid with a parameter, something I would call it's still a god. Yeah. And the same.
It seems like, I mean, I just want to push you on this a tiny bit. It seems like if I give you an explanation for C, it seems like no explanation I give you will satisfy you. Like if I look at the wave speed of any wave in a material, it's a product of the density and the stiffness of that material. So I could easily deduce from that principle that what light speed is telling me is the stiffness and density of the medium by which light is being transmitted, and that the atoms being made out of the same substance are subject to the same speed limits. And that makes perfect logical sense to me. And I'm not saying it's true. I'm just saying it at least follows from those first principles.
Mm-hmm. No, I mean, there are, so to speak, two hearts in my chest. I mean, I love the idea. I mean, I love the analogies. I even, I have argued that these tell us something very deep about nature, the analogies with topological defects and speed in a medium and so on. But still, it's at the very end, it's still a shortcoming of these ether models that I mean, you shift the explanation elsewhere. Instead of asking, where does the speed of light come from? I mean, at the end, you have to ask, where does the density and where does the stiffness come from? And who made that up, these numbers? So I admit that, I mean, would be fine. I mean, I would be happy if you left those constants. Don't get me wrong.
Well, what they tell us is
I'm
that
with you.
they
I'm
tell
with
us,
you, but
it's
still, I
extremely
mean,
fast,
still
right? It's the
maybe not the end of the story. It's still not, maybe not the end of the story.
Well, then you have to start asking, what is the material? What is the organization of the material? How does it bend? What are the parts of it? What is the source of it? You're not at the end, and there is some thought that Gödel's incompleteness theory says that you can't get to the bottom because you get to a place where you have to start with, well, there is something.
Yeah.
Right, because I think that the
Some
fundamental question
things.
is, why is there something rather than nothing?
Some things.
Yeah. But I mean, the really most modest set of assumptions, I mean, it's okay. It's very modest. Can assume it's ether-like, but still, I think it's not entirely satisfactory. Let's say at least consider the possibility that C is something, indicates something we have not understood yet, instead of being that fundamental property of space-time, be it the speed of light or be it the stiffness or whatever. And the same thing is with H. I mean, classical physics didn't need H. It was a surprise. It was unexpected. It was an anomaly in the sense of Thomas Kuhn. And it was resolved. I mean, all the quantum theory is fantastic, but why it's fantastic? Because it boiled down this plethora of concepts to just one constant. Okay, it's fantastic that you have these appearances of H in so many different contexts, but it's an anomaly. It's an extra parameter. It's still a modern godness, this H. So
does unification lead to a single parameter then? I mean, so it's like, we talked about theories of everything and what is the goal of the project.
No, I pulled you to the edge of Silla, but just, I mean, let me finish that. I mean, the idea of, I think the idea is somehow attractive, that you want also to explain this 3 plus one dimensional structure of spacetime, and that leads you to consider to a couple of mathematical constructions, such as complex numbers or quaternions. Here we are. Quaternions are the most simple four-dimensional structure. Unit quaternions, the three-dimensional structure. They have this very naturally emerging property of being split into 3 plus 1 dimension. And they have an intriguing property, which is somehow related to the idea of H and spin and non-commutativity. Yeah, it's non-commutativity. Quaternions, unit quaternions, the multiplication does not commute. That means A times B is not B times A. And this is what reminds you from operators in quantum mechanics. If you commute the, say, angular momentum operator in x and y direction, they do not compute at the z angular momentum. So I somehow would like to entertain the idea, already still on the first level, let's say, no real sound theory behind, but I would like the idea that this existence, the very existence of H, is somehow related to that property of non-commutativity in quaternions. And just to remind you, quaternions may look very similar to space-time, because it's a three-dimensional quantity, and it may look like R3 and a parameter time, but it's not. There's no proof that this Newtonian idea of an Euclidean R3 and with a time attached is the most appropriate description of reality. It might well be another mathematical structure that hopefully then could even provide a reason for the existence of these fundamental constants.
I think we need to put you in touch with our friend Thad Roberts. Have you heard of him?
No, but I'm always saying I need help from mathematicians here at this point because it's becoming incredibly difficult. But
He's working on a project where he's trying to simplify the constants of nature, and he's trying to find relationships between them and figure out how to basically push this into the next direction. And I think that you guys might find.
He has a whole think tank set up in Utah that are working on this same problem. I think you guys would have a great conversation. Yeah. It's too bad you can't make it to our conference because he's going to be there, and I think it would be a great discussion. But maybe in the future we'll get you guys together.
Yeah. I really value the way that you think about these questions, and that you spend so much time putting this out into the world, and your explanations are always really well structured. And I love how in your videos, when you make a video, you tie it to the other ones that you've done, and so it's easy to go from one video and then there's an entire playlist and you can see how your thinking has changed over time. And I don't know, I always really enjoy talking to you. It's really I appreciate that we've found you.
Yeah, I mean, we all try to make sense of this. I think this is the interesting challenge, and we are privileged to being able to dedicate our time to this stuff. And of course, I mean, everybody can be mistaken, but we shouldn't. I mean, we just should ponder these. These are the big questions, and I mean, yeah.
What can we look forward to next on your channel? What are you working on? Are you working on some papers as well?
I'm working on a paper. I mean, I'm trying to make to get a little bit more down to earth, analyzing supernova data and try to provide evidence for this variable speed of light. I'm arguing that could be easier interpreted in terms of variable speed of light. And then I have one more video about the sun, and one more methodological video about why I'm doing science on YouTube. And then let's see next project. But this is, I mean, the thinking about the mathematical structures that can possibly be could possibly replace that 3+1 dimensional picture of space-time postulated by Newton is one of the central issues. But you can't do this all the time, because it's just too frustrating in a way, because you really need. I mean, you don't have results for months and years, and so it's also you need to do also something else.
Yeah, definitely.
Like regarding the sun, really quick before you go, do you think that is it possible to publish a paper about the liquid sun? Do you think that there's actually a journal that would take anything about that?
Well, look, I mean, I'll talk also about that peer review. I mean, Pierre has done wonderful work, laid out in great detail with perfect quotations, went on the history. Every line is well argued, and so what else do you want? And he published it in Progress in Physics. And if some now mainstream solar physicist comes along and then, no, this is not what I think is a good peer-reviewed journal, so what the hell? I mean, I really wouldn't care about that. That being said, it's also, I mean, sometimes nice to get the attention also of other people, of course. But it's important to get the message out, and And well, that's an entire new story about organization of science and overflow of information, and how can we handle all this.
It
Maybe
happens
we need
so
also
often
new
that
means in that direction. Yeah.
whenever I talk to anybody who isn't acquainted with the black body issues with the solar spectrum, I often people will say, "Wow, you should write that up and send it to Scientific American or publish. Why haven't
Nature.
why hasn't anybody published? Yeah, send it to
Review.
Nature." Yeah, I just it's an intractable issue. I'm curious if you had thought about.
You want the answer? I mean, why not physical review? The fundamental idea? Well, because physical review is full of blah blah blah, Browns, Galileans, supersymmetry, in 26 dimensions. And not only that, I don't like the content, but just 1,000 pages every 2 weeks, and that's just intractable. So
Well, thank God there's YouTube.
Yeah.
For now.
I like the I think it's a Chinese proverb. It says when the leaves are sinking in the water to the bottom of the sea, the stones come up. And making the analogy, you have all these conventional peer-reviewed renowned journals with so much nonsensical stuff in there, so maybe it's a good idea even to keep away from that kind of science, because we need a revolution in any case.
Amen.
So that can't be the solution.
Hopefully we'll be able to
Or do you think that tomorrow, in tomorrow's issue of Physical Review, the theory of everything will eventually be published and every physicist will immediately make sense of it and understand it? Do you believe that?
No, but something like
the methodology.
but something like the liquid sun just seems so, obvious from really simple first principles. At least it's very bizarre to me. I feel it's very surreal that it isn't being entertained seriously in the astronomical community. All of these other things require a lot of abstraction and complicated math, but that's one theory that I just am sort of shocked by, because most scientists I explain it to who aren't astrophysicists are like, "Wow, that's a cool idea. Where is this where can I find, and of course I can point them to Pierre, but it's it's sort of the one that I just can't get over how simple it is, and you can't find it in the literature. Very strange.
No, we do have a problem in the organization of science. That's clear, but that's another topic I would suggest to discuss.
People can read what is it? Make Physics Great Again. Yeah, I think you lay it out fully.
Yeah.
This is the cause of everything that we're doing, right? We started this podcast because we called it DemystifySci because we wanted to deal with the mystification at the heart of physics. And we've branched out to a bunch of other topics, but at the end of the day, this was the
at the end of the day, it's a really exciting time to be alive. Like, I always think that sometimes, like, I'll just be on the phone with Pierre or something, I'm like, holy crap, this is crazy. Like, people 1,000 years are gonna talk about this, and it's just it kind of just trips me out sometimes, like how amazing it is that we're alive in this time where so much.
Don't appreciate,
nobody knows, right? Like, most people aren't aware that these revolutions are happening beneath the surface of the water, but it's pretty remarkable. It's kind of exciting also.
I actually think that we need to hire a stone carver and start leaving stone tablets etched with these ideas all over the place. Because I'm like a
basic formulas, I would say.
Right? Like the Voyager plaque, but for the liquid metallic sun. I think that this is the direction we need to take these things in.
No, but you're doing a great job. I really enjoy the conversations because, you're very receptive and open to new ideas and ask great questions, and I also I'm inspired by that and pondering and reflecting. That's all what we can do. Okay,
indeed. Hopefully we can do it again
it's
soon.
good to be on the same team, Alexander. And I wish you the best of luck. I'm really looking forward to what comes next from your pen. And have a great rest of your night.
Thank you.
Thank you, sir. Bye, everybody.
Good night.